Howdy folks, and welcome to part 9 of my comprehensive guide to pfSense 2.3. In this video, I'm going to be going over the traffic shaper. So to give you a bit of an overview of what you'll see in this video, first of all I want to go over what traffic shaping is, and I'm going to go over some broad traffic shaping theory because I think it's good to know and understand what's going on under the hood. I'm going to go over limiters because they are the simplest form of traffic shaping you can apply. I'm also going to go over the ATLQ schedulers. I'm going to go in depth into service curves because they are required by one of the ATLQ schedulers. Of course, I'm going to go over configuring limiters in the web UI, as well as using the traffic shaping wizard, and manually adding custom shaping rules in the web UI as well. So we need to define what traffic shaping really is. And ultimately, traffic shaping is the act of controlling the bandwidth or latency of one or more traffic flows. And this is usually done for quality of service control. But you can also perform traffic shaping to simulate network conditions as well. And so the guiding principle we're going to be following is that we want to delay less time-sensitive traffic to improve the overall performance of time-sensitive traffic. We can control latency quite easily by adding a simple first-in, first-out queue or buffer. So basically packets are temporarily stored in a queue and then they're released to their destination at some later time. Now, in a normal network, we generally want to minimize this queuing delay. And in fact, a theoretical ideal network actually doesn't have queues at all, but in practice that's not possible. We would require infinite network bandwidth for that to be possible. And we can use queues in a couple different ways. First of all, we can delay packets for when the network is less congested. So we hold on to packets when the network is busy, and then we can release those packets at a later time. And that, of course, allows for more important traffic to pass by. And we can also use it to simulate longer network paths, which can be quite useful if you're testing an application or a service, whether you're a developer or you're simply testing something. If you need to simulate what will happen if you're connecting, across the world to something on the server on the other side of the world, you can simulate that propagation delay by basically adding a queue with a delay. Now, bandwidth control is a little bit more complicated, and we need to start out by classifying bandwidth somehow. Now, normally we would consider a data rate when we talk about bandwidth, something like bits per unit time or maybe packets per unit time. And I differentiate these because, of course, packets are not always the same size. So these are not directly comparable units always. But you can't really just use a data rate to describe bandwidth. It's actually far more complicated than that. And as an example, take two different rates, 1 packet per second versus 60 packets per minute. They sound the same, but they're actually not. They have the same average rate, but they have very different characteristics. And so we ultimately need more than one data point in order to describe bandwidth. When we're controlling bandwidth, we want to consider a few different parameters. The first one is, of course, the average data rate. This is the long-term data rate. This is kind of, I'll call it the sticker bandwidth. This is what we refer to usually as bandwidth. But we also have the burst rate, and this is the maximum rate that is achievable at any particular instant in time, which is usually higher than the average data rate. Of course, when we have these bursts, we have to look at how much data can be in a burst, and we call that the burst length. And of course, how often these bursts can occur is the burst frequency. And I want to make it very clear that bursts do not violate the average data rate. A lot of people think that these bursts are over and above the average data rate, but that's not really true. And to sort of explain that, I'll just show a quick example. So imagine that we have two different traffic flows. Traffic flow A, where we have 1 packet per second, and then flow B, where we have packets grouped like this. You'll notice that both of these flows have an average packet rate of 1 per second, but flow B has a burst rate of 4 packets per second. So the average rate is conserved even though the burst rate exceeds the average rate. It's only the way that the packets are arranged in time that changes. So I want you to think for a second about how we would actually design something that can implement bandwidth control taking these parameters into consideration. And so I want to go into a little bit of an aside on sort of a very common method used for doing bandwidth control, known as the token bucket regulator. So in a token bucket regulator, we have a bucket, and we have a FIFO queue, and we plumb it together. We add in a token factory, and bingo, we have a token bucket regulator. So let me explain how this works. This is a very common construct. It's very commonly used in networking, and token bucket regulators also find other uses, which I'll maybe go into in just a moment. So first of all, tokens are added to the bucket at the average data rate. So if, for example, we wanted our average data rate to be 1 token per second, then we would add tokens to this bucket at a rate of 1 token per second, assuming that the bucket was not full. If the bucket's full, we don't add anything. And the bucket size corresponds to the burst length. So in this trivial example, we'll say that we can only hold 2 tokens in the bucket. And so in this case, the bucket is currently full. The basic principle of operation is that packets come in from the network and they're placed in the queue. The packet that's at the front of the queue requires a token in order to be forwarded out to the network. So in this case, there is a token available. The token is taken from the bucket, the token is destroyed, and the packet is forwarded out to the network. And so as a result, we can burst at any given moment in time. If there's 2 items in the queue, because the bucket size is 2 tokens, we can burst 2 tokens out of the regulator. However, if we have packets constantly coming into the queue, we can only release them at the average rate of 1 token per second, because that's what we're adding to the bucket. And so this allows you to, the average rate is always conserved because the token factory always produces tokens at the average rate, but you can burst because of the tokens in the bucket. And it's a very simple regulator, and it's used very commonly in networking. One other place where it's commonly used is in embedded systems. I know this isn't going to be applicable to a lot of people that watch this, but if you ever work in embedded systems, if you have a microcontroller or something that has an interrupt to service routine, you can of course have what's known as an interrupt storm, where basically some fault condition creates a massive number of interrupts which can swamp your processor and ultimately cause your device to crash. And so you can actually use a token bucket regulator to regulate the amount of interrupts that come into your system to prevent an interrupt overload. So these are a very simple construct to write programmatically, but they are quite useful, and they work very, very well. And pfSense does the low down in FreeBSD. These are used, but we're not really going to be dealing with these directly. But just so you get an idea of what's going on, this concept is definitely used. So with that aside out of the way, let's move back to the main focus of this video, and let's go over limiters first of all, because limiters are ultimately the simplest form of traffic shaping. The principle of operation is that you define one or more of what are known as pipes, and each pipe has a maximum bandwidth that's associated with it. And the idea is that a pipe cannot use more than its associated bandwidth. You write some firewall rules which classify traffic, and it assigns that traffic to a particular pipe. And so therefore, you can restrict the bandwidth of those traffic flows to the bandwidth that you've set for the pipe. So I want to make note of something right off the bat, and that is that limiters are not work conserving. So what that means is that a pipe can never exceed its bandwidth, even if there is available bandwidth on the parent connection that the pipe runs through. So even if you could be sending data faster than what you specified as the bandwidth of that pipe, it won't happen. And so this leads to a waste of your precious networking resources. Generally speaking, you're going to be doing traffic shaping or limiting on a WAN interface, right? It's going to be your internet connection that is going to be the narrowest and most expensive link that you have. And so generally speaking, you don't want to underutilize that, right? And so limiters don't work terribly well in this case, because if you decide to limit some particular type of traffic, you may you may end up underutilizing your network. So for general quality of service and those types of things, limiters are not what you're looking for. In pfSense, limiters are implemented using DummyNet. So if you want more information about limiters, I recommend you look for that in relation to FreeBSD. One thing that's very important to note is that pipes don't discern between packet direction. So what that means is that you will need two pipes, one for inbound traffic and one for outbound traffic, to get a proper full duplex connection. Now, there's nothing wrong with assigning both traffic directions with your firewall rules to the same pipe, but you're going to end up with a half duplex connection in that case, which might not be what you're looking for. Another thing that's worth noting is that DummyNet can implement what's known as a dynamic limiters. So basically, it creates pipes on the fly for individual hosts, so individual IP addresses. So you can imagine a situation where you can set it up so that every IP has its own bandwidth limit without you having to write a separate rule for each IP address separately and add a separate pipe for every IP address separately. So it has that functionality, and I'll show you that in the web interface. So with limiters out of the way, we now move on to the ATLQ schedulers. And this is where things get far more interesting. Now, pfSense has 5 built-in options for doing traffic shaping. And they are CODEL, FAIRQ, PRIQ, CBQ, and HFSC. Now, of course, CODEL is kind of the odd one out here, but I don't really have a better place to put it, so I'm going to group it in with this, because this is kind of how the web interface groups stuff together. And all of these are recommended for general quality of service tasks. And I'm going to be covering these starting from the simplest to the most complex. So that's why I've chosen this ordering, because we're going to kind of be building our knowledge as we go. And hopefully this will make sense. I might put timestamps in the description if you want to jump to a particular scheduler, but you may need information from a previous one for things to make sense. So jump ahead at your own risk. I want to make a note right at the beginning that more complex is not always better. A poorly configured complex scheduler will likely perform worse than a well-configured simple scheduler, despite any of its downsides from being so simple. So if you choose to use a complex scheduler, you should be prepared to tweak it a lot before it works properly. And also, you know, on the same grounds, if you choose to use a simple scheduler, just make sure you understand what its weaknesses are, and so that you understand if it really is the right choice for you. Now, one thing that we will see a lot of is the notion of queues, and so I want to make a few notes on queues before we get started. All network interfaces have a queue for outgoing packets, right? So this is sometimes referred to as the transmission buffer. And normally packets are treated in a first come first serve basis, right? The first packets that arrive in your pfSense box, doesn't matter where they come from, are the first ones that get added to this queue, and then they shuffle through the queue in a FIFO manner, and then they're released out onto the wire. And all traffic shaping really does, on like the most simple fundamental level, is it just simply uses an algorithm to select the order of packets to add to that queue instead of doing it on a first come first serve basis. That's really what we're trying to do. We're just trying to reorder that queue, basically. That is what traffic shaping does. There are a few other things we can do to that queue, as you'll see in just a moment, but generally speaking, that's really all we're doing. So the first thing that I want to talk about is CODEL, which stands for controlled delay. And this algorithm is not really a traffic shaper like the others, but again, sort of due to the way it's grouped in the web interface, I thought I'll talk about it now. Its goal is to reduce buffer bloat, and I'm going to explain what that is in just a moment. It's the absolute simplest thing that you could possibly add to your network, because there are no firewall rules that you have to add to set this up at all. And as a result, it doesn't differentiate between types of traffic. In fact, it only has one option that you can set, and that is the available bandwidth on your link. So all you have to do to get it to work is tell it how much bandwidth your connection has. So if you've got a 50 megabit per second internet connection, you just tell it, I have a 50 megabit per second internet connection, and that's all you need to do. Simple as that. It can be enabled on any interface, and it's something that even if you don't watch anything else in this video, you should probably think about adding this just because it's so simple. Now, of course, it's not perfect. It doesn't work well on slow links. So I would say roughly anything below 0.5 megabit per second, you should probably not turn CODEL on for that. And it also doesn't work well for big links as well. So if you have a large amount of bandwidth, maybe you're a company, an organization, something like that, a data center, probably you don't want to use it for that. You should use something more complicated. So of course, what is buffer bloat? What is this thing that we're trying to reduce? Well, buffer bloat is basically the act of having consistently full network packet buffers on an interface. So just like I said how all interfaces have a queue for outgoing traffic, buffer bloat is when that queue, that buffer, is consistently full or near its maximum capacity. And having these large buffers, these large queues, it increases network delay for pretty much all traffic because all the traffic has to sit in these queues for a longer amount of time. And ultimately, it doesn't really increase overall throughput, it just causes congestion. Now TCP, the Transmission Control Protocol, it has some simple congestion avoidance built into the algorithm, but large buffers, they can defeat the algorithm and it ends up making things just much worse. And so what CODEL does is it's designed to drop packets in those queues to prevent buffer bloat from happening. And it works by measuring the travel time of packets in a queue. And it discards packets to keep it at a reasonable size. So basically, it measures how long it takes for a packet between the time it enters the queue and the time it exits the queue. And if that time is too long, then it starts to discard packets based on some sort of mathematical model. And as a result, by keeping the queue smaller, it will improve the overall latency of the network. And like I mentioned earlier, if the network link is slow, large packets, so ones with large payload, so ones that are close to 1,500 bytes or jumbo frames even, they actually can take so long to shuffle through a queue that they can actually cause false positives and they can false trigger packet drops. And so this is why I don't recommend that you use CODEL on slow network links because you may end up actually hindering your performance. So the first kind of real traffic shaper is FAIRQing. And FAIRQing, as the name implies, is designed to give all connections fair access to a queue's bandwidth. And because this works on a connection by connection basis, this shaper doesn't work well for applications which create lots of connections. For example, I'll use BitTorrent, right? It's fair if every person or every application has 1 or 2 connections. But if one application just opens 100 connections, then of course it's going to be able to swamp the link because it now has 100 times more bandwidth than anybody else. So that is one of the big downsides of this type of scheduler. I also note that it's not perfectly fair, but that's by design. And I'll mention that FAIRQ is work conserving, which means that it will always transmit data if there is data to be transmitted. So unlike a limiter, you won't have an idle network connection when there is data to be transmitted over it. So FAIRQ is implemented by creating 1 or more queues for a particular interface. And then there are some firewall rules which group traffic into those queues. And every connection in each queue is then hashed, and it's placed in a hash bucket. And so when I say every connection is hashed, you can think of it like the IP address and the port for every it sort of uniquely identifies a connection. And so that's what gets hashed. And so it sort of splits up all of the packets into some fixed number of buckets. And then those buckets are serviced round robin. So what I really mean by that is that packets are forwarded by drawing 1 packet from each hash bucket in turn. And so this roughly translates to 1 packet per connection per cycle. And so therefore, every bucket, every connection should theoretically get the same amount of service if they have the same amount of traffic. Now, it's not perfect because there, of course, are a finite number of buckets. And so it's very possible that there will be a hash collision and that you may have two connections which end up sharing the same bucket. And it's also possible that one of those connections might have a lot of traffic and the other one might have a lot less traffic, and so therefore it may get swamped out by the other connection. So it's not perfect, but it works generally okay in practice. So the next scheduler is known as priority queuing, and as the name implies, it attempts to separate traffic based on priority. And so the architecture is as follows. We have two levels of nested FIFO queues, and there can be no more than two levels, so it's basically a flat architecture. The first level is always known as the root queue, and this queue is set for the total bandwidth that's available on the link. And when I say set, I mean the system administrator, aka you, tell the system what the total bandwidth available on the link is, and that root queue is sized accordingly. Below the root queue, you can then have two or more child queues. And each of these queues has a priority from 0 to 7, with 7 being the highest priority. And the principle of operation of the scheduler is that packets are drawn from the queue that has the highest priority. In the event that that queue is empty, then the next highest priority queue is emptied, and so on and so forth. In the event that you make two queues which have the same priority, then they get emptied in a round-robin fashion, assuming that traffic is available. And so since traffic is always forwarded, if it exists, then PRIQ is work conserving, right? It will always forward something if any of the queues have traffic in them. So let's give a little bit of a graphical example here. So let's say that I have three different queues, which I'll call class A, B, and C, and they all have different priorities. And then of course we have our root queue, which is the parent to all of these. And so all of these three child queues, they flow into the root queue. And so what our algorithm is going to really do is it's going to be picking which packets from which of these child queues make its way into the root queue in what order. So let's add some arbitrary traffic here. So each of these boxes represents a packet that's sitting in each of these queues. So because class A has a higher priority than the other two, packets will be pulled from that queue first. Now once that queue is empty, we're going to start pulling from class B, of course, because that has the next highest priority. And at this point, the root queue is full. We've saturated our link bandwidth, and so we can't really forward anything any further. But let's say sometime later, the packets, they get forwarded out the link, and some more packets arrive in the class A queue. So we have to take those higher priority packets. And I think you can kind of already see what the problem, the biggest problem with this scheduler is, and it's known as starvation. It's possible that packets in a lower priority queue can sit potentially indefinitely in the presence of a stream of higher priority traffic. And so it's not a fair scheduler is really what I'm trying to get at. And you can have these problems where you get massive latency on low priority traffic. The next scheduler addresses this starvation issue, and it's known as class-based queuing. And so this is similar to PRIQ in that we have nested FIFO queues. However, there can be more than two levels. So you can actually nest child queues, basically, if you want to build a more advanced scheduler. The first level, of course, is always the root queue, same as for PRIQ. And of course, you can then have two or more child queues, and those queues can also have child queues as well. And similar to PRIQ, each queue has a priority from 0 to 7, 7 being the highest priority. However, the big difference is that every queue also has a bandwidth, and it's set up such that the sum of all of the child queues' bandwidths equal that of the parent queue. So if you only have two levels, all of the child queues' bandwidths must add up to the root queue. And so the principle of operation here is that packets are drawn from the child queue with the highest priority until its bandwidth limit is reached. So this is what allows us to get rid of the starvation problem. Now, child queues can also borrow bandwidth from their parent if available, and you'll see that in our next example. And since children can borrow bandwidth, CBQ is worth conserving. So let's go over a simple two-level tree example. I think most people will probably start out by just doing simple two-level trees. So of course, our first level, we have our root queue, and let's assume that this is our WAN interface, and we have a 50 megabit per second internet connection. So that's the amount of bandwidth we have to go around. So I'll define 3 different queues for 3 different services, and I'll give them their appropriate bandwidths and priorities. So SSH, it's a real-time protocol. I mean, it's interactive, so you want that to be as responsive as possible, so we'll give that a high priority. HTTP, it's sort of user interactive, so we want that to be relatively high priority as well. And BitTorrent, we don't really care about it. It's just a thing that happens in the background, so we're going to give that the lowest priority. And the bandwidths, SSH, it's relatively low bandwidth, so we'll just put in 100 kilobits a second. HTTP, could be multimedia going over it, we don't really know, so we'll just give it a whole bunch of bandwidth. And BitTorrent, give it some small bandwidth so it has something. Now, every queue is guaranteed its bandwidth, but they can borrow from their siblings if available. So assuming HTTP isn't using all of its available bandwidth, BitTorrent could use that, or SSH could use that, whatever's left over, in order to keep the scheduler work conserving. So just because we've said 5 megabits per second for BitTorrent doesn't mean that's what the limit is. That just means that in the event that all of the other services are using all of their allotted bandwidth, BitTorrent is only guaranteed that much. And the priority is basically used to allow you to control the latency. So the higher the priority, the lower the latency will be during times of congestion. So you want your more real-time services to have higher priorities. And I think that makes logical sense. So at this point, there's only one scheduler left, and it's arguably the most popular and most complex. And so before I go into discussing it, I want to talk about service curves, because they are fundamentally important, and I think I need to spend a little bit more time on this than anything else, because I really want you to understand service curves before we get into the scheduler, because if you don't understand service curves, none of this is going to make any sense. A service curve basically defines when incoming traffic receives service. So by service, we mean when the traffic is chosen to be forwarded out of the router. And so I'm going to be explaining service curves using graphical examples, because I think that is the easiest way to understand this, rather than looking at equations. Now, I'm going to assume that you've taken high school math and that you know linear equations and how to calculate slope and things. So this is a classic depiction of what's known as a linear service curve. So on the x-axis we have time, which is usually in milliseconds or seconds, and then on the y-axis we have service, which is usually represented in bits. Now, physical links and limiters have linear service curves like this, where they have a single straight line. And so the way that you kind of read this is that as time passes, the number of bits that are forwarded over a link, for example, it trends up linearly, right? So if you have a 50 megabit per second link and you send traffic constantly at 50 megabits per second, then the number of bits that are transmitted in total will go up in a linear fashion. And as a quite nice result of this, the slope of that line is actually the bandwidth of the link, right? Because of course we have bits on the y-axis and seconds on the x-axis, right? And slope is rise over run, so it's bits per second. So the steepness of that line is the bandwidth of that service curve. And I'll mention that the root queues in any of the previous schedulers I've talked about have this type of a linear service curve, because of course they are directly tied to a real link and therefore they have a set fixed bandwidth. So let's do a little bit of an example, and let's assume that we have traffic that arrives at a rate of 10 packets per second. So its arrival curve, this is not a service curve, its arrival curve would look something like this. So if it's 10 packets per second, we'll say one packet comes every 100 milliseconds. So if we were to graph the number of bits over time, it would look something like this. Every time a packet arrives, we have this vertical edge of where all of those a number of bits arrives. The number of actual bits doesn't matter. It's not important. But that's what our arrival curve would look like. Now, if we add a linear service curve that has the same average slope, so what I mean by that is the slope of our service curve is the same as the packet arrival rate, it would look something like this. Now, because packets leave the queue according to the service curve, we can actually measure the queuing delay that would be present in this case by effectively sort of sliding over where the arrival curve intersects the service curve. So we're kind of looking at the Y projection. And so in this case, the delay that we would observe is 100 milliseconds per packet. So from the time the packet arrives, which is the vertical jumps in the sort of the step function of the arrival curve, if we slide that over, if you follow the arrow to where it intersects the service curve, that is the amount of time that that packet would sit in a queue before it gets forwarded out. So if we sort of graphically depict that, if we have our packet arrivals and departures, and every color represents a different packet, we can see that the packets arrive and depart at the same rate. So there's no need to drop packets or anything like that. However, the packets get delayed by the service curve by 100 milliseconds, which just in this case happens to correspond to the arrival rate. But what if this is a problem? What if the latency that we incur, like the 100 milliseconds in that example, what if that's too big? What if we need a lower delay for something that's real time, such as VoIP, for example? Well, if we use a linear curve, we use a straight line, the only option we have is to increase the slope. Now, if we do that, that will reduce the delay, as I'll show you in just a moment. But it also has a side effect of increasing bandwidth. So here you can see that we have the same packet arrival curve as before, but we now have a steeper linear service curve. And you'll notice that by doing this, the delay is reduced, but the bandwidth allocation has also increased. And so we're actually allocating more bandwidth than we need. We're allocating 15 packets per second. That's the slope of the service curve. But the packets aren't arriving that fast. And so we've allocated more bandwidth than we need, which therefore doesn't really allow us to provision our network very effectively. So if we graph that like we did previously, you'll notice that the queuing delay approaches 0 because we've under-provisioned our network. Now, of course, it doesn't actually reach 0, but just for this example, let's just say that it does. So the fundamental takeaway from this is that with a linear service curve, latency and bandwidth are interdependent on one another, i.e. you cannot reduce delay without also increasing bandwidth. Now, of course, you may say, well, what if I have a service that needs low latency but also doesn't need high bandwidth? Like, let's take SSH, for example. Ideally, we would want to somehow be able to decouple delay and bandwidth. And we can do this. What we need to do that is known as a non-linear service curve. So the key is to use a piecewise dual slope linear function. So we draw it as follows. We have one line segment which has a slope known as M1, and then we connect another line segment with a different slope of slope M2, and the point where they meet, the x projection of that point, is a time value known as d. And so we can characterize this entire function by three quantities, M1, M2, and d. So with those three numbers, the two slopes and the time at which they intersect, we can basically just write down or enter in this service curve. We don't need any more equations than that. So if M1 is greater than M2, i.e. the first line is steeper than the second line, the curve is known as a concave service curve. And vice versa, if M1 is less than M2, the curve is known as a convex service curve. Concave service curves reduce delay, and convex curves increase delay. But of course, both must exist in any traffic shaping scheme. Because of course, not everything can be high priority. Priority is relative. So if you make some things concave, you must make others convex, or otherwise everything will just end up having the same priority and nothing will change. Now let's redo the previous example with a nonlinear service curve and see what happens. So we have our same packet arrival curve as before, and we have a concave nonlinear service curve. Now you'll notice that the slope M2 is the desired average bandwidth, which is 10 packets per second, like we did in the very first example. But the slope M1 is higher in order to reduce the delay, and so it's 15 packets per second. And so as a result, the delay in this case is actually 50 milliseconds per packet. And so if we graph this, as we did before, due to the fact that we have a concave curve, our average bandwidth is the same as the first example, right? There's no drop packets, there's no wasted bandwidth allocation. But our delay is 50% less than that first example. And as a result, we have successfully decoupled delay and bandwidth. Now, as with life, there is no free lunch. If you use concave curves, you must balance them with convex curves. Now, ideally, the sum of all service curves should actually be a straight line to match that of the service curve of the root queue. But in practice, this is not required and doesn't really make a lot of sense because there will be time delays between when service curves start. They're not going to be tracking perfectly in line with each other. So let's take a look at an example. So let's say I have this black service curve and this blue service curve. One of them is concave, one of them is convex, and they both start at the same time. So what I mean by that is there happens to be two different traffic flows, one for each, and both of those traffic flows happen to start at exactly the same moment in time, and so these service curves are tracking with each other. Now let's say that the root queue has a service curve represented by this red line. Now let's say that at time t, which is some arbitrary time later, we have this other service curve. There's this other traffic flow which has a different service curve, and it's in green. Now the problem here is that in order to guarantee, in order to satisfy that service curve, we would actually need the root queue's service curve to follow the dotted line in order to satisfy that M1 bandwidth, which of course we can't do. We can't have more than 100% bandwidth. And so we actually we can't guarantee all of these service curves 100%. It doesn't exactly make a lot of sense to try and make all of your curves add up to a straight line because ultimately traffic is going to be starting and stopping all the time, and so therefore they're never going to really be lined up, and so the algorithm is constantly going to have to be adjusting the service curves to make them fit. And so with all of this talk of service curves out of the way, we can talk about the last scheduler, and that is the Hierarchical Fair Service Curve Scheduler, or HFSC. And it builds on the architecture of class-based queuing. But it extends it by adding a nonlinear service curve, and it uses a dual slope piecewise function as we described earlier. So I want to go over this one by way of example. So we'll do a two-level example. Let's say that we have, of course, the same root queue as before, 50 megabits per second, and then we're going to have 3 child queues, but instead of priorities and bandwidth, they're going to have service curves. And service is ultimately given according to these service curves, but of course queues can borrow from other siblings if available, just like they could in class-based queuing, and so of course HFSC is normally work conserving. Now note that SSH is convex, and both BitTorrent and HTTP are concave. In fact, BitTorrent actually has an M1 slope of 0, which means that it's guaranteed that all packets will have a delay of at least 50 milliseconds in that case, because no packets will be forwarded for the first 50 milliseconds. Now you may notice that the M2 values in this example actually do add up to the root queue bandwidth, and of course the M1 values don't, but the M2 values do. And I recommend following this, this principle because if you have a bunch of sustained traffic flows across all of your different queues, you want your traffic shaper to be sane. You want to have allocated bandwidth, according to a percentage of 100%. You don't just want random values. If your M2 values, if your sustained bandwidths exceed 100% of the root queue bandwidth, then it doesn't really make a lot of sense. And it will still work because HFSC will compensate and it will make decisions, but it probably won't make the right ones. So as I've just said, the M2 values should probably add up to the root queue bandwidth. But the M1 values don't necessarily need to do the same because, of course, with time shifting, they can never really be guaranteed anyway. Now, HFSC generally works on a best effort basis. So it tries to satisfy everyone's service curves while sharing bandwidth effectively. However, it's not perfect. And so we can actually make it better by providing more information to the algorithm. And we can do that by defining additional service curves. In fact, with HFSC, every queue can actually have 3 different service curves. The first one is known as the link share service curve. The second one is the real-time service curve, and the last one is the upper limit service curve. Now, the service curve that I've been talking about without giving it a name is the link share service curve, because that one is required. The other 2 are completely optional, but they do have some benefits if you define them. So the link share service curve is kind of like the normal target for the algorithm. It's what I've been talking about previously. It will attempt to do its best to satisfy that service curve, and it will also borrow. It can exceed that service curve by borrowing bandwidth from other queues and adding that bandwidth onto the link share service curve. The second service curve is known as the real-time service curve, and this is effectively a minimum amount of service that you can reserve for a particular queue, i.e. it is guaranteed and it cannot be borrowed by any other queue. Now, if you do this, just note that adding this can make the scheduler no longer work conserving, because you're now reserving bandwidth that cannot be borrowed by any other queue, regardless of whether it's in use or not. Generally speaking, real-time service curves are good for real-time services. So if you have VoIP, for example, and you have a minimum bandwidth that it can operate on, you may want to define a real-time service curve for that particular queue, such that VoIP will always function and you won't have any dropouts. If you have some sort of telephony that has different levels of quality, where as the bandwidth goes down, the call quality goes down, well, you might want the minimum level of call quality to be your real-time service curve and the sort of desired level of call quality to be your link share service curve. So in a worst case scenario, you drop down to the real-time service curve and you have a reduction in call quality, but you never have drops because that bandwidth is reserved. The upper limit service curve is kind of self-explanatory, and it is a maximum amount of service that your queue can borrow from any other siblings. And so as a result, it kind of acts like a limiter. It's the maximum amount of bandwidth or service that can be given to any particular queue. And you could use that if you wanted to restrict a particular service from just constantly flooding your network, for example. And again, if you add this curve, it's possible that the scheduler will no longer be work conserving, because of course that queue may not be able to use bandwidth that's available to it. So with all of the schedulers out of the way, I want to just give a few quick tips on designing and implementing traffic shaping. Some of these are probably common knowledge, but I might as well go over them anyway. First and foremost, know your network. If you don't know what's going on your network, then you have absolutely no hope of being able to shape it. And so as a result, Wireshark is your best friend. I recommend that you observe traffic in production and take captures of that traffic for debugging later. Once you have those captures, once you've observed what your traffic looks like, make some assumptions and guesses on how you can improve performance of whatever it is you're trying to achieve, and then build a shaper with one or more of the shapers I've previously discussed. Once you've built it, you're ultimately going to need to implement it. So you know, you're going to need to test it, and you can test it in one of two different ways. You can either test it in production, which may sound bad, but in certain circumstances that may be viable. Just turn it on and see what happens. Worst case scenario, it crashes and burns and you turn it off again. Or you can test in isolation. And so this is where those captures come in. You can basically replay those network captures that you took on production, and you can observe what happens to them. And you can do that in one of two ways. You can either replay the traffic, and then you can actually try to use the network, try to use interactive services and, you know, observe what happens, or you can replay the captures and then on another machine on the other side of, you know, your pfSense box, you can then do another capture, and then you could actually sort of compare the two and sort of look at you know, mean latencies and things like that, and see if things actually got better. Now, just note that if you try to test in a virtual machine, just understand that on most hypervisors, the virtual network interfaces don't actually operate at their real speeds, and therefore that may skew your results by quite a bit. Network interfaces, they can run really as fast as the CPU or RAM will let them. So a gigabit interface in a VM is not actually a gigabit. It can do 4 gigabit, it can do 6 gigabit. So that may change things. And also the latencies, if you're using, especially if you're using like an internal network, some sort of virtual switch, of course the latencies are unnaturally low. And so that can also affect how your shapers behave. So with all of that kind of theory out of the way, I think now it's time to move on to the web UI, and we'll go over all of the options and how you can actually implement all the things that we've gone over in the actual interface itself. So I'm here at the web interface for my virtual machine, which I use to screencast these videos from. So I want to go over configuring limiters first of all, because that was the first thing I went over in the video. And you can get to the limiters by going Firewall, Traffic Shaper, and then clicking on the Limiters tab. And as you can see, I have no limiters currently configured, so we want to add a new limiter. So the options that you see here are basically for the pipe itself. So of course, we want to enable it, and we want to give it a name. So I'm going to call it something very generic for this video, but of course you would name these with reasonable names. And then of course we define a bandwidth for this pipe. So let's just say 100 kilobits per second. So you know, maybe double dial-up for this example. And of course, if you had schedules defined, you could add one here. And you can also add multiple schedules. So if you had, so for example, if you wanted this pipe to change bandwidth depending on the schedule, you could have different bandwidths associated with different schedules, and as long as they don't overlap each other, you can have basically the bandwidth of the pipe change over time. These two fields here, these are the mask for dynamic pipe creation. So I mentioned that DummyNet has the ability to dynamically create pipes based on IP addresses, so you don't have to create pipes manually for each host. So if you leave the mask at none, then this remains a simple pipe with no dynamic features. However, if you change the mask to either source or destination address, then for every packet that passes through the pipe with a different source or destination address, then a new dynamic pipe will be created for all traffic either to or from that address. And of course, DummyNet needs some way to distinguish between hosts, and it does this by you providing the subnet mask effectively, so that way if there's a change outside of that mask, then it knows that it's that's the host portion of the address, and that it should be given a different pipe. Of course, as usual, I always recommend putting in a description for your reference in the future, because you're going to forget what this thing does, especially with stupid names like this. But of course, this is a demo. I'm not going to bother to give it a description. And then there are some advanced options down here at the bottom. The first field is delay in milliseconds, and like I said, you can use limiters to simulate poor connections. So just like I'm simulating 100 kilobits per second here, I could be restricting some traffic to that bandwidth, or maybe I'm trying to test something, And so if you leave this blank, it's assumed to be 0, so no added delay. But I could put in, 200 milliseconds worth of delay to simulate, some very long network path, across a country or something. Or in fact, actually, that's more like a transatlantic cable, pretty much, with that kind of latency. Similarly, we can simulate packet loss as well. And so this is basically just a probability. So it ranges, is a floating value between 0 and 1, 0 meaning no packet loss, 1 meaning 100% packet loss. And so you can put in a decimal value here if you want some random packet loss to simulate, again, a poor connection. The last two fields are sizes for the queue and for the hash buckets. I recommend probably not touching these unless you have problems. Their units are slots, and you'll see this throughout the web UI. And slots basically means packets. So the units are packets. Basically, one slot can hold one packet regardless of packet size. So that's what that means, in case you're wondering. So anyway, I don't want any dynamic features, so I'm going to just turn this off, and I'm just going to click save. Actually, yeah, we'll leave the delay on. Why not? We'll just click save, and I'll apply those changes. Why not? So here I have one limiter, which I've called limit 1. And so if I actually go into diagnostics limiter info, I'll just open that in a new tab, you can see that we now have one limiter, which is in our 100 kilobits per second, 200 millisecond delay, and it's all good. Now there's one thing that I didn't mention earlier, and that is that you can nest queues within limiters. So right now I have a single pipe with 100 kilobits per second bandwidth, and I could assign traffic directly to this pipe, but I could also create one or more queues that sit within this pipe and that share the bandwidth of this pipe. And you do that by going to the bottom and clicking the Add New Queue button. And so now you'll notice that I have pretty much the exact same options, except I can't specify a bandwidth anymore because the bandwidth is already defined by the parent of this queue, which is the limiter I just created. So the idea is that each queue has some weight, which is basically a percentage value of the full bandwidth of the parent pipe. So you could have several queues, each with a different weight, and therefore they'll use up to that percentage of the pipe's bandwidth in the event that they're all being utilized. So it is work conserving in the sense that if there's only one queue with traffic, even if it has a low weight, maybe lower than the others, it will still use the full limiter's bandwidth in the event that there's no other competing traffic with a higher weight. So let's just enable the queue here. And of course we don't want any dynamic features. And I'll give it an arbitrary weight of, let's say, 50. Let's say I don't need anything else. And I'll hit save. And now you'll notice that there is a nested queue below our limiter. And now if we actually look at the limiter info, you'll notice that now there is another queue here, and it has a weight of 50. And so I can continue to add more queues and I'll give it a different weight. And so now you can see we have multiple queues, and you can see they have different weights. So all of these queues are limited to a combined maximum of 100 kilobits per second. Now if you remember, I mentioned earlier, in order to get a proper full duplex connection, you need to have two different pipes, one for incoming and one for outgoing. So I can create a second limiter and give it some bandwidth. And so now I'll just create another queue below this. And we'll give it arbitrary weight. The weight doesn't really matter if you only have one queue, because of course it's going to have 100% of the bandwidth, but I'll just put it in there for no apparent reason. So at this point, we've created some limiters, but they don't actually do anything because they don't have any traffic flowing through them. So in order to change that, we need to create some or modify some existing firewall rules in order to ensure that traffic flows through these limiters. So if we go to firewall rules, we have two options. We can either add the limiters as a advanced option to an existing rule, or we can create some floating rules which match the traffic. So let's say that I wanted all of my traffic on my LAN of course, that passes through the router to be limited by those limiters that I just created. So I'm just going to pick the allow LAN to any rule, and let's edit this. And if we go down to the advanced options, you'll notice, as I mentioned, I believe in my last video, the in and out pipe. And so now there are some options for this. So the way that this works is described in the help text here, but basically the first option is the input pipe. So this is the data that's coming into the specified interface. So because we're editing the LAN, then of course this is things that are coming into the LAN interface, and this would be things that are leaving the LAN interface. And of course you only specify the outgoing if you specify the incoming. And there is kind of a weird caveat with floating rules that because floating rules, you can specify their direction to be outbound, you can specify them to have the opposite direction. These fields actually become reversed. So if you have a floating rule whose direction is outbound, then the one on the right is actually the incoming, and the one on the left is actually the outgoing. And of course the labeling doesn't change, you just have to know that implicitly. So it does say it here, but it is kind of an odd thing. Floating rules, the interface doesn't change based on what you set the direction to, so you just have to kind of do that reversal in your head. So I'll specify the incoming pipe as one of the queues from the first limiter, and the outgoing will be a queue from the second limiter. So therefore we'll have a proper full duplex connection. And if I save this, it will ask me to apply the changes, and I'll do that. And so now all of the traffic for that rule passes goes through those two queues. So now we should have effectively a 100 kilobit per second full duplex connection. So we can test this by going to basically anything, because of course I've added this to the the allow to any LAN rule. All traffic that matches this rule, all traffic that's passed by this rule will be affected. So there's no traffic flowing through it right now because of course we can't see any flows that are being limited. But if I open something, maybe speed test, everything is going to be incredibly slow because of course we're simulating 100 kilobits per second. And some things are actually going to be relatively fast because some of this is cached. But we'll see if this even loads. I may have to speed this up. And so if we go back, you'll notice that now we're dropping packets in both of those queues as expected. And of course this is very, very slow. So I don't even think I'm going to do this. I think you get the idea. It is working. So I'm just going to remove those limiters from this rule, just because it makes things a little difficult. Okay, so if you wanted to create your own rule that doesn't already exist, I would recommend creating a floating rule. And so basically all you would need to do is specify the match action, which of course is not going to change the flow of the traffic, but it will flag it so that it gets picked up by the limiter. And you would make, all the rest of this you would select it based on whatever traffic you were trying to limit, and then you would of course set up the pipes as before. And like I mentioned, if you're using an out direction floating rule, just remember that these are backwards. And that way, this way, of course, you could create a rule which doesn't actually affect the flow of traffic. It doesn't affect any existing rules that you may have under your interfaces, but it will shape them. So I think that's it for limiters. Let's move on now to the ALT-Q schedulers, which is, of course, what people really want to see. And I think the way I'm going to go about doing this is I'm actually going to show you the wizard first of all, show you what that creates, and go from there. So as you'll notice, there are two wizards. One of them is called multiple LAN WAN, the other one's called dedicated links. Now, pretty much everybody, regardless of how many WANs or how many LANs you have, you're going to select the multiple LAN WAN wizard. It has a terrible name. It's just been called that forever. I don't really know why it's never been changed. So that's what we're going to be going through. So the first thing that we have to enter, of course, is the number of WAN-based connections we have and the number of LAN interfaces that we have. So in this case, we have one WAN, and in fact we do have two LANs because, of course, we have this optional interface as well. So these numbers are actually already correct. And so now we get to pick what schedulers we want for each of the interfaces. So in this case, for our LAN, let's say we want HFSC, and for our optional interface, we also want HFSC. But of course, we can pick between class-based queuing or priority queuing if we want to use one of those simpler schedulers. And for the WAN, we have a few extra options specifying what the upload and download speeds are. And so in this case, these numbers all are already correct. So if you have a VoIP system, you can choose to prioritize that traffic over others, and if you do this, of course, you'll have to specify all of your details as well as speeds for your different interfaces for this VoIP traffic. I don't have this, so I'm just not going to fill it in, so I don't even know what I would populate here. You have the ability to set up what's known as penalty box. So basically, this just creates a rule to limit the bandwidth for a specific IP address. This is useful if you have some host that you want to restrict its traffic to by a hard percentage. It's, I think, most useful if you just want to turn this on just to see what it generates, and then you can sort of use that as a template for generating your own rules later on. So I will just leave this. I've already pre-configured this. And next is peer-to-peer networking. So of course, generally speaking, we would want to lower the priority of peer-to-peer traffic. So of course, you can enable this if you want. This P2P catch-all basically is for all traffic that is uncategorized. You can choose if you want to consider it peer-to-peer traffic. I personally don't like this, but if you're, depending on the network, it may actually be worthwhile doing so. And of course, you can specify which protocols you want rules to be created for, because ultimately what this wizard does is it creates a floating firewall rule for each protocol that you select. So of course, really, you only need to select ones that you know exist on your network. So let's just say that I only really have BitTorrent on my network, none of these other ones. So it will create a rule, which we'll see after the wizard's complete, which pertains to BitTorrent. And of course, the next one is gaming. And so of course, we can prioritize gaming. Of course, we want to reduce the latency, so that's what we're doing here. You can specify, again, which services you want. And of course, you can pick whatever you want, and it will create rules for each of these. And then there's a list of games which it has sort of predefined rules for, and of course you can of course add rules for your own games if they're not in this list, which I suspect will probably be the case for a lot of people. But it's very easy to add your own rules, so don't worry if what you want is not already here. This is kind of an old wizard. The next page is for sort of just general applications, and so you can basically specify priority levels for just certain sort of applications that this wizard knows about. And so you can specify whether you just basically want higher or lower priority for each of these different services. And so I'm not really going to bother to change much here. I'll just say that, you know, HTTP should maybe be higher priority, and maybe, I don't know, crash plan backup should be lower priority, you know, Samba higher, whatever. I've just created just a couple here just to show you what this generates when the wizard's complete. And once you're done, you just click the finish button and it will actually create all those rules for us. And so it gives us a little bit of like sort of a log message which shows what it's done, and it says that it's complete. And so now if we go to our traffic shaper, you'll notice that a whole bunch of stuff has been created here in the interface view. You can also look at it by queue. So basically both by interface and by queue, or for the alt queue schedulers, it's basically the same information but displayed in a different way. The by queue doesn't have the ability to sort of edit anything. You have to go to the by interface view to actually get panels where you can edit things. So I'll come back to this in just a moment. I also want to show you what has been created in the firewall. You'll also notice if you go to floating rules where there were no rules before, you'll now notice that there is a large list of rules that were created by that wizard. So if we go to the traffic shaper, so you'll notice at the top level we have WAN, LAN, and opt1, and these are the root queues for each interface. So if I click on WAN, you can see, of course, we can enable and disable the scheduler on that interface. We can change its type between any of the types I mentioned before. And so this is the bandwidth, this is the root queue bandwidth that is available on this interface. Of course, because I have a 10 megabit per second upload, that is the bandwidth that's available on the WAN. And queue limit, and this is TBR, this is token bucket regulator size. I would recommend probably not changing these because you almost always will not need to. So because this is HFSC, of course, we can have nested queues below the root queue. And so we have another queue called queue internet, which is below this, and then we have a bunch of queues which are also nested below that. So we have two levels in this nesting arrangement. Of course, we can enable and disable this queue, we can give it a name, and then we've got a bunch of options. And I want to make note of something right away, and that is what this interface effectively is doing is it's generating a bunch of command line arguments for the low-level FreeBSD traffic shaping utilities. That's really what this does. And so this interface is designed to make it easy to translate, you know, what's in these boxes into a command line, you know, a set of command line arguments that can be passed to this utility. And so it's not the most user-intuitive interface. And there are also a few things that I really don't like about it, a few things that I believe are actually wrong. And the first thing is this priority help text here. And you'll notice it says, for HFSC the range is 0 to 7. This, I believe, is wrong because HFSC, if you remember, doesn't have priorities at all. HFSC uses service curves to determine priority on a case-by-case basis. Now, what I believe this should say is CBQ, the range is 0 to 7, because in CBQ, that is correct. So I believe this help text is actually wrong, so don't let that confuse you. Now, one thing that I will note is that you can actually put a number in this box, even if you have an HFSC scheduler. You can put a number in this box and it will not return an error, but that priority will be ignored by the actual scheduling utility. So this box has no effect if you're using HFSC, and so that's why this is very confusing to me. It doesn't make any sense. So if anyone actually knows what's going on, please let me know. But to the best of my knowledge, that's a bug actually. So if we were using CBQ, you would enter your priority for this queue in there. Queue limit, this is basically the size of the queue in packets or slots for this particular queue. If you leave it empty, it uses a system default. We have a few options for this queue. And first of all, there's of course CODEL, so we can enable CODEL on this queue, as I mentioned earlier. And we have RED capabilities, random early detection. And what RED really tries to do is it tries to prevent the queue from reaching its size limit before it actually reaches its size limit. And so CODEL sort of works by a time basis, and RED works by a size basis. And so you can enable RED for incoming packets and for incoming and outgoing packets if you want. ECN, explicit congestion notification, this sort of works hand in hand with RED, and in the event that congestion occurs, it can set a flag in the packet header to sort of notify other routers downstream that will be receiving that packet that congestion is present on the path. And of course, this only works, it only does anything if the router downstream has support for reading that flag and actually doing something about it. But in my opinion, it doesn't hurt to set the flag, and so it is actually set by default. So you can choose what you want to do with those flags at your leisure. Of course, set a description for it, I'd recommend. And then we have this bandwidth field here. And this is the second thing that I think is really dumb about this interface. Because of course, here we have our service curves, which we can specify. We have, of course, the upper limit, the real time, and the link share service curve, which are exactly as I mentioned earlier. We can enter in our M1 values, our M2 values, and our D value, which is in milliseconds. And so, of course, we don't need anything other than the link share service curve, but we can add in these other ones if we wish. Now, there's also this bandwidth field, and so we never really needed a bandwidth when we were dealing with service curves earlier. So what's the deal with this? And according to the source code, what actually happens is this box, this bandwidth field, is actually the same as the link share M2 box. These are actually the same thing. And so if you put a value here, you don't need to put a value here. And similarly, if you put a value in this bandwidth field, it overrides what's in this box. So if I put a different value, let's say 15, in this box, then even though my link share says 10 megabits on M2, it will actually be 15 megabits on M2. And that's not documented anywhere, which is really dumb. So I would recommend basically don't put anything in this box if you can, and that way it'll just be less confusing and it'll use this value. And if you do put something in here, just make sure that it's the same, so therefore there's no confusion. Now the other thing that you'll notice is that there are no M1 or D values for these service curves. And that's because you don't necessarily need them. If you want just a straight linear service curve, all you need to do is enter in the M2 value, and it's assumed that that's the slope for the entire curve. Only if you want to make it nonlinear do you add in the M1 and D values. So by default, the wizard doesn't actually create nonlinear service curves. It only creates linear service curves. And so you would have to specify that D value if you wanted to change these around. So now let's look at another nested queue below this queue internet queue. We'll look at queue default. And this one, of course, this one has a priority value, which will be ignored because we're using an HFSC scheduler. I believe these priorities are put in place because the wizard doesn't really care whether you're using HFSC or CBQ. It just populates them regardless. So that's why that's there, but of course that doesn't have an effect. You'll also notice that now that we're nested another level, we have this other option here called default queue. And so basically, the default queue receives all traffic that is not explicitly put in another queue by a firewall rule. So this will have, basically, this is the catch-all for all traffic that is not explicitly shaped. And of course, it has all sort of the same parameters as before. Of course, these values are all generated by the wizard, so I haven't entered these in, and I kind of disagree with some of these. And of course, it was created one for peer-to-peer, one for games, one for what it calls other applications, high priority, and other applications, low priority. And then there's this other queue called QAC. And I think I've mentioned this in a previous networking video, but whenever you are transmitting data using like TCP, for example, in one direction, there is a constant stream of acknowledgement packets which are headed in the other direction to inform the sender that the receiver has actually gotten the packet and it was not corrupted. And so you have to ensure that those acknowledgement packets get back to the sender in a timely manner, because the sender uses that stream of acknowledgement packets to figure out how fast it needs to send packets to the receiver. Right? If it doesn't get a lot of acknowledgements back, then it knows that not a lot of the packets it's sending are actually making its way to the receiver, and so it'll throttle back. And of course, we don't want that to happen. We wouldn't want the sender to throttle traffic to us because we can't send acknowledgements fast enough. So generally we put in a queue specifically for acknowledgements, and we give it actually a relatively high priority because we want to ensure that we tell other servers that we are receiving data and to keep it coming at the maximum rate that we can accept. So that's why there is an acknowledgement queue in fact all of these on all of these interfaces. Now for LAN, of course, similar thing, HFSC, it has put in our 100 megabits bandwidth in kind of an odd manner, but that's what it does. So one thing that you'll notice, which is different between the LAN interfaces and the WAN interface, is that the WAN interface has this queue default nested below queue internet, and the local interfaces don't have a queue default. They instead have a queue link, which is actually up one level. And this queue link is actually the default queue for these LAN interfaces. They have a queue limit probably to prevent buffer bloat, would be my best guess. I'm no expert, so I'm not entirely sure why the wizard does that. And this is effectively the catch-all for both of these local interfaces. So now let's take a look at the firewall rules that were created by the wizard. So of course they're all floating rules, and of course, as you saw before, they're just a bunch of match rules. And the description of these rules is kind of a machine parsable format, which of course is human readable, so you can tell what these rules do. So let's just pick one here. Let's look at the Minecraft TCP outbound rule. So all this rule is really doing is simply matching traffic that comes in on the WAN that's TCP, and it's destined for this particular port. And I haven't played Minecraft in a while, but I'm going to assume that that is the Minecraft port. Of course, it has a description, and the most important part of the rule, of course, is the queue setup at the bottom. So the queue, which is on the right-hand side, this is, of course, where which queue the traffic will go through. And on the left-hand side, you have the acknowledgement queue, which is optional, and this is the queue which all of the ACK packets that are generated from the incoming traffic will be passed out through. So if you don't specify this, if you leave this none, then the ACK packets will go through the default queue. But of course, since we have queue ACK on the WAN, we can use that to, of course, shape those acknowledgement packets accordingly. And of course, it doesn't make any sense to specify an acknowledgement queue if you don't specify another queue, because it doesn't make a lot of sense to shape just the ACKs. And I don't even think that that is actually officially supported doing so. So, of course, there are going to be rules here for all of the different things that we selected in that wizard. But there's a few things that I want to sort of point out. A lot of these rules kind of look like they are duplicated, but they really aren't. For example, this peer-to-peer rule here, it's not actually duplicated because the protocol is different. One is TCP and one is UDP. Similarly, Steam, of course, there's one for UDP and one for TCP. And you'll notice, this is actually a good example, the UDP one does not have an ACK queue specified, but the TCP one does. And of course that makes sense because TCP, of course, is a connection-based protocol and it has acknowledgements. UDP is connectionless. There are no ACKs on UDP, so it makes no sense to specify an ACK queue for a UDP rule. So that's what that's done there. Another thing that I want to point out is, of course, if this isn't already obvious, there is no deep packet inspection going on here. traffic is sorted into queues based exclusively on these rules, which are almost always using the port as the way to separate traffic. So if you go through that wizard and you select that you want to lower the priority of BitTorrent traffic, if your BitTorrent client doesn't use any ports in this range, then it's going to have absolutely no effect for you. So make sure that you either create your own rules or you edit these rules to change the port range to be in accordance with the software that you're actually using, because otherwise these rules, they won't have any effect. And of course, you can add your own rules to match traffic on whatever interfaces you want, and then you can, of course, specify the source or destination ports, and then you can pick your own queues accordingly. It's very easy to add your own rules, and you can view the status of this by going to Status Queues, and here you will see all of the queues and the number of packets per second and the bandwidth that's currently being allocated to each of these queues. And you can see the length of the queue. So the default queue length is 50 slots, 50 packets, except for, of course, those queue link values, which I pointed out earlier. They were set by the wizard to 500 slots. You can view how many packets have been dropped in each queue and how many time slots have been borrowed from other queues due to link share. So this is of course quite boring because there's really no traffic going through this VM at the moment. But I recommend that once you make changes, you just take a look here and see if things look right. And if they do, then you can actually, if you really want to, get out Wireshark or something and check if it's made a difference to your latency or whatever it is that you're trying to do. But if it doesn't look right here, chances are it probably isn't right, and it might save you some time. I'll also point out that in the Traffic Shaper, of course, you can view this by queue as well. And so all this really does is it just offers a summary, really, of sort of the most important parameters. But of course, it doesn't actually, it doesn't show you the service curve info, and it doesn't allow you to change anything. So it's just a way that you can sort of quickly at a glance see sort of the most important parameters. But really, I think you really need to go into the byte interface to see what's going on. If you want to get rid of the shaper, of course you can delete queues and things manually, but the easiest way is to actually click the Remove Shaper button right here. So if you use the wizard and you ultimately decide you don't want to do this, or you want to build everything yourself from scratch, you can just click Remove Shaper, and when you do that, it removes all of the rules, sort of all of the queues, sorry, and it also removes all of the floating rules that it created as well. So it won't remove any rules that you have created, but it will remove all of the ones the wizard created. So it's sort of an easy way to just get rid of everything if you want to start over. So yeah, I think that goes over everything that I wanted to cover today. And so as always, thanks for watching.